Let's start with a review of the formulas that were presented in the other video. If you did not write them down during that video, I would suggest that you grab a piece of paper and a pencil and do the job now. So the two types of energy that we're going to be able to calculate right now are kinetic energy and gravitational potential energy. These are methods of storing what we call mechanical energy. Later on, we'll add one more, which will be the elastic potential energy. We also talked about moving energy into a system and away from a system, and that was called work. Okay, so work isn't like a different type of energy, it's just the way we describe energy that's being transferred into or out of a system. And sometimes you'll calculate that by knowing a force and a displacement, and sometimes you'll calculate it by looking at how the energy changed, looking at the starting energy and the final energy and subtracting those. And then we also described that there is a rate at which work is done, so that involves time. And it's just simply dividing the work or dividing the change in energy by the amount of time that the transfer requires. All of the ideas of energy are measured in joules. So kinetic energy, potential energy, and work are all measured in joules. And then power is joules per second, which is called a watt. So here's a first question. Let's think about what formula we would need in order to solve this and how we might do some algebra to determine the mass. We'd want to begin with the kinetic energy formula, m times v squared over 2. And you could certainly plug things in and then do your algebra, or you could do a little math to start with and see that the mass would be 2 times k divided by v squared. And again, the new variable here is the capital K. That stands for the kinetic energy. Plugging everything in, making sure we square the value of speed, we would get 4 as our answer. And because we were looking for a mass and we use standard units, it would be in kilograms. If that toy airplane is known to be 5 meters above the ground, we could also find its gravitational potential energy now that we know the mass. We would use this formula for potential energy. Again, capital U is our symbol for all of our potential energies. One thing we need to remember is that the value of little g is not going to show up in the problem. We need to know that since we're on Earth, that is 10 newtons per kilogram. And so overall we'd get 200, and our standard units for energy are joules, abbreviated capital J. All right, so this question talks about work. And again, there are two ways of thinking about work, either in terms of a force and a displacement, or looking at how the energy of the system is changing. In this case, they're asking us for a force. And so we would begin with this version of the work formula. And again, you might want to rearrange it, do the algebra first, and see that the force would be the work divided by displacement. And then that would come out to be 180 newtons. Again, if you put standard units into a formula, you get standard units out. This problem asks us to sort of think about work the other way, in terms of that work changes something's energy. In this case, the problem is talking about changes in speed, and so this would be a case where we'd want to think about the change in energy as being a change in kinetic energy, meaning that we'd want to subtract a final value, k, minus an initial value, k sub 0. Some people like to use K sub F and K sub I for final and initial. That's fine, use whatever symbols make the most sense to you. In this case, because the boat starts from rest, that initial kinetic energy is actually 0. So basically, the amount of work we were given in the beginning of the problem, 5,400 joules, is the final value of kinetic energy. So now we should be able to determine the speed. Again, we'll grab our kinetic energy formula. We can either plug things in, or I'm going to rearrange to find V first, practice my algebra here a little bit. So I would multiply both sides by 2, divide by m, and then square root to find the speed. Again, standard units in, standard units out. So this would be 5.2 meters per second when I do my algebra. All right, let's take a look at this work problem. So in this case, again, I could think about this in terms of forces and distances, or I could think about it in terms of the type of energy that's changing. And that's how I'm going to approach this. Since the position is changing, that means the potential energy is changing. And so I'm going to think about this as work equals change in potential energy, meaning that I would want to subtract the final potential minus the initial. The formula for gravitational potential energy is m times g times y, where y is the vertical height above some lowest point. There are a couple of ways that you can approach this question, but a common way is to just assume the ground is the 0 point and to measure all of your heights relative to that. So there would be an initial potential energy of 9 times 10. Remember, 10 comes from the gravitational field strength on Earth. So 9 times 10 times the initial height, which is 0.5. And then to repeat that calculation, just using 1.7 as the height instead. So these are our two values of y. And then to find the change in potential energy, we just subtract the values. And that determines our work. So that comes out to be 108. By the way, another approach would be to first subtract the heights and then just do the potential energy calculation once. But this is a more, I don't know, let's say it's a safer way of doing it, because sometimes it works to do that subtraction first and sometimes it doesn't. And so this is the way that will always work for you. Now, if this process requires 1.5 seconds, we can determine how much power was needed. Power is the rate at which energy is being transferred. So in this case, we can just think about this as work over time, since we've already calculated the work. So that's the 108 joules divided by 1.5 seconds. And a joule per second is stated as watts. Now officially, the abbreviation for watts is a capital W. But because capital W is also a symbol in our formulas, I like to write the word watts out. That way, there's lots of confusion as to which W I'm talking about. Entirely a preference, but that is something, a habit I've gotten into to avoid making silly mistakes like thinking work and watts are interchangeable. The other unit for power is the horsepower. So let's just take a quick look at what this value would be in horsepower, in case maybe you're familiar with those sorts of numbers. 1 horsepower is 746 watts. And so we can set up a conversion so that the units are set up diagonal from each other and see that this is a pretty small amount of horsepower. Usually things done by a human are. You really need some sort of engine for it to be a significant amount of horsepower. So just a quick summary that delta E or W can be found in a couple of different ways. Sometimes we're just going to use the formula that most people think about when they think about work: force times displacement. But you don't always have that kind of information in a problem. Sometimes you're given information about the speed of an object before and after something happens. Sometimes you're given information about the height of an object before and something happens. So if the problem is talking about lifting and you're given information about the change in position, then you may end up wanting to do it this way. You might end up looking at the change in gravitational potential energy. Note too, though, that since mg together is the weight of the object, and that's how much force you would need to lift it, some people actually do think about these lifting problems using this formula as a force times a displacement. There's kind of two ways of looking at it. But if you do have a situation where the object's speed is changing, you really have no choice. You have to think about what the final kinetic energy is, what the initial kinetic energy is. Again, here I'm showing it with F for final and an I for initial because some people prefer that. Some people just like to use V and V sub O. Okay, so it's kind of just a preference as to what makes more sense to you. But it is important to notice that you can't just subtract the values of V. Because they're squared in the formula, you really have to take the time to calculate individual values and find that change in kinetic energy. But however it is that you have found the work or the delta E, if you're asked to find power, you take that value over time, and that will tell you the rate at which energy is being transferred.